Now, I have the uniform continuity. Okay, and in the uniform continuity, before going to give the formal definition of the uniform continuity, we consider a real valued function, or we can examine a real valued continuous real valued function f from the closed interval -1 to 1 to r, which is defined as f of x is equal to x square. Okay, so we are considering a function f from the closed interval -1 to r defined by f of x is equal to x square. Let x naught be any points of this closed interval -1, 1. Then we will see that d f of x naught with here is r with the usual matrix. So this d is the usual matrix, and therefore this is equal to mod of f of x minus f of x naught. But f of x is equal to x square, so this is your x square, this is your x naught square, and this is equal to mod of x minus x naught into x plus x naught. Okay, and this term is less than epsilon whenever x minus x naught is less than 1 over 2 epsilon. Why we are taking 1 over 2? Because the length of this, that x plus x naught. So x and x naught are the elements of the closed interval -1 to 1. So the distance between x and x naught cannot exceed more than 2. So that's why this cannot exceed more than 2. So we can say that this term is less than epsilon whenever x minus x naught is less than 1 over 2 epsilon. So you can say that this is 1 over 2 less than epsilon, it is equal to, and now we can choose 1 over 2 epsilon is equal to delta. Okay, so in other words, we can say that x minus x naught is less than delta. Okay, then the d f of x naught is less than epsilon. So if this is true, if f mod of x minus x naught is less than delta, then this is less than epsilon. It means that the function f is continuous. But the important thing is that we will see here is that this delta is depending only on epsilon, not the point x naught and x. Okay, so here is delta is depending only on epsilon, not x naught and x. Now if we consider the same function, okay, so for every epsilon positive there exists a delta which is equal to 1 over 2 epsilon, such that for any point x naught in the closed interval -1 to 1, we have d f of x naught is less than epsilon whenever d x naught is less than delta. It means what? It means that the function is continuous. But again, I am emphasizing that delta is depending on epsilon, not on the point x and x naught. Now if we consider the same function, f of x is equal to x square on the whole metric space R with the usual metric. Okay, that is f is a function from R to R, which is defined as f of x is equal to x square. Then for every real number x and x naught, we have again d f of x naught is equal to mod of x square minus x naught square, and then again as above, this is equal to mod of x minus x naught into x plus x naught. Okay, and this is less than epsilon whenever x minus x naught is less than 1 over mod of x plus x naught. Okay, so if this term is less than epsilon divided by mod of x minus x naught, then this term this is less than epsilon whenever this is less than this term, and now this is we can call is equal to delta. And now here you can see that this delta is depending on epsilon as well as on x and x naught. Okay, so this delta is depending on epsilon as well as on x naught. So here is we can say that the uniform continuity say that of course in both the cases function is continuous. Function is here is also continuous, function is here also continuous. Because for every epsilon positive there exists a delta is greater than 0, delta is greater than 0 such that f of x naught is less than delta. Okay, implies that d f of x naught is less than epsilon. So the function is continuous, but the difference is what? Difference is that here the delta is depending on epsilon, not on x and x naught. But here is delta is depending on epsilon as well as on x naught. Okay, so if this delta, okay, works uniformly for every element x naught. Okay, it means that if delta is independent of x naught, okay, then we say that the function is uniformly continuous. Okay, so if delta is independent of x naught, that is to say if delta depends only on epsilon, not on the point x naught. So in this way we see that delta may depend not only on epsilon but also on x naught. So uniform continuity is essentially continuity plus the added condition that for each epsilon we can find a delta which works uniformly over the entire space, in the sense that it does not depend on x naught. So that is the main thing between the continuity and the uniformly continuity. So a function f from a metric space X to a metric space Y is said to be uniformly continuous if for every epsilon positive there exists a delta positive, where delta depends on epsilon only, okay, not on the point x and y, such that for every x and y in X, the distance between x, y is less than delta, implies that the distance between f of x and f of y is less than epsilon. Okay, so if you put two definitions, the definition of continuous function and the definition of uniformly continuous function, you will see that we say that for the continuous function we say that a function f from x to y is continuous at a point x naught if for every epsilon positive there exists a delta positive. Okay, so in that case delta is depending on epsilon as well as on delta. Delta is depending on x naught as well as on epsilon. But here is we say that if for each x epsilon positive there exists delta, and delta is not depending on any element x and y, it is depending only on epsilon, such that this implication holds good. So it is very means you can see that if delta is working for every x and y in capital X, then we say that the function is uniformly continuous. Now here is we can see that very easily every uniform continuous function is continuous. Okay, but the converse is not true in general. So as we have seen in the previous example, here is you can see both the functions are continuous. Okay, but this function is uniformly continuous. Why? Because delta is depending only on epsilon but independent on x naught. And in the second example, delta is depending on epsilon as well as on x naught. So here is the function, this function f from R to R, which is defined as f of x is equal to x square, is continuous but not uniformly continuous. And this function defined, but only the thing is the function f defined from the closed interval -1 to 1, okay, in the same way that f of x is equal to x square it is uniformly, of course it is continuous and also uniformly continuous. Here are some few examples you can see. So take X is any discrete metric space and Y is any metric space, then any function f from X to Y is uniformly continuous. That is to say, every function from a discrete metric space X to another metric space Y is uniformly continuous. The second example, consider X is equal to open interval 0, 1 with the usual metric induced by the usual metric on R, and Y is equal to set of all real numbers with the usual metric. And the function f is defined from X to Y as f of X is equal to 1 over X for all x's in X. Then this function is not uniformly continuous. Why it is not uniformly continuous? You can see that let us take epsilon is equal to 1 over 2 and delta be any positive number. Choose X is equal to 1 over n and Y is equal to 1 over n plus 1, where n is a positive integer such that n is greater than 1 over delta. Then we can see that X minus Y, okay, X minus Y is equal to 1 over n minus 1 over n plus Y. You simplify, it is equal to 1 over n plus 1, and this is less than 1 over n, and we are choosing that n is greater than 1 over delta, so 1 over n is less than delta. Okay, so it means that this is what, so X minus Y is less than delta, but you can see that f of X minus f of Y is equal to, because X is equal to 1 over n and f of X is equal to 1 over X, so f of X when X is equal to 1 over n is equal to n, and similarly when Y is equal to 1 over n plus 1 is equal to minus 1 is equal to 1 n plus 1. So n is, so it is equal to 1, but this is greater than epsilon, because we are choosing epsilon is equal to half. So thus whatever is lambda greater than 0, maybe there exist X and Y such that X minus Y, the distance between X and Y is less than delta, but the distance between the images of X and Y is greater than 1 over 2. Okay, and therefore this function is not uniformly continuous. Okay, so you can see that no polynomial function of degree greater than 1 is uniformly continuous on the usual metric space R. And of course, we note that any polynomial is a continuous function. Again, the logarithmic functions is not uniformly continuous on the whole space, metric space X, which is equal to open interval 0 to infinity. Okay. Okay, let's take a theorem which says that if f is a continuous function from a metric space X to a metric space Y, and X is your compact, then f is uniformly continuous. That is to say, as we have seen here, every uniformly continuous function is continuous, but the converse is not true, as we have seen, because here we have defined the function from X to Y and X. Okay, so this function is not uniformly continuous. Now the question is, under what condition the converse can be true? That is, under what condition a continuous function can be a uniformly continuous? And the condition is very simple. If the metric space X, okay, and f is a function from X to another metric space Y is continuous, then it is uniformly continuous. So if X is your compact space, Y is any metric space, f is continuous from X to Y, then f is uniformly continuous. And now you can see that here in this case X is equal to open interval 0, 1. So this is not a compact space, so we did not get the continuity. Okay. So, of course, here this function is also not compact, so we did not get the uniform continuity. Okay. So, to prove this one, that f is uniformly continuous and is let epsilon is greater than 0 and x be arbitrary. Consider the image f of x and the open sphere with center at f of x and radius epsilon. Okay, then this set is your open set. The function is f is continuous. So, continuous image of open set is open and therefore f inverse s epsilon f of x is open in x. Okay, so for each x we are getting an open set in x. It means that this family, okay, will form an open cover. Okay, so these are the this will form an open cover of x. Okay, this is then this an open cover of x. And now since x is compact, okay, so it is sequentially compact, and therefore we have by the Lebesgue covering lemma, there exists Lebesgue number delta is greater than 0 for this open covering. Okay, thus for every open sphere of diameter less than delta, every open sphere of diameter less than delta will be contained in at least one member of f. And consequently, we can take that the open sphere with center at x and radius delta y2 must be a subset of f inverse as epsilon f of x. And now you operate f both the side, we will get this thing. Now, what does it mean? The meaning is that hence for each epsilon positive, there exists a delta, okay, delta bar, delta tilde is greater than 0, which is independent of x. Now, here is for epsilon positive, there exists delta tilde, okay, independent of x, such that dxy is less than delta y2, which is equal to delta tilde, and imply that d f of x f of y is less than epsilon. So, here you can see that this d tilde, okay, independent of x. So, this the distance between x and y is less than d tilde, implies that the distance between f of x and f of y is less than epsilon. It means that the function f is uniformly continuous. Now, take an example. Consider the space CAB. CAB means set of all real valued continuous functions defined on the closed interval AB with the metric d infinity, which write d f of g is equal to maximum of f of t minus g of t. And note that because the function f, okay, in CAB is a function from a compact set AB to R, because these are f is what? F is a continuous function defined on a closed interval AB. So, closed interval AB and it is bounded, so in R it is compact. So, f is a continuous function from a compact set AB to R, and then from the above theorem, every continuous function is uniformly continuous. So, the element of this space are uniformly continuous. Okay, keep in mind the elements of this CAB are uniformly continuous. However, we have seen that in remark 4.3 that CAB is not sequentially compact, and therefore it is not compact. Okay, CAB is not compact, but the element of CAB are uniformly continuous. We can easily prove that the composition of two uniformly continuous functions is a uniformly continuous function. Okay, so it is very simple one. Now, as I mentioned in the theorem that the continuity of a function is equivalent to say that if xn converges to x implies f of xn converges to f of y. Okay, so this we have seen. The continuity means xn converges to x implies f of xn converges to f of xn. So the continuity means continuity is equivalent to this one. Now the question is that can we say that if xn is a Cauchy sequence, then f here is means that if xn is a convergent sequence, then it is same as to say that if xn is a convergent sequence, then f of xn is also a convergent sequence. Okay. Now what about the Cauchy sequence? Whether we can say that because if xn is a Cauchy sequence, then f of xn is also a Cauchy sequence. Okay, this we can prove that only if the function is uniformly continuous. So, if xn is a Cauchy sequence, then f of xn is also Cauchy sequence if f is uniformly continuous. So this statement we prove here is so let us take f is uniformly continuous. So for each epsilon positive there exists delta positive depending only on epsilon, such that for all x1 x2 in x the distance between x1 and x2 is less than delta, implies that the distance between f of x1 and f of x2 is less than epsilon. In particular, we can take here is we can take xn and here we can take xm. So here is we can take xm and xm is less than delta, implies that the distance between f of xn and f of xm is less than epsilon. And now since xn is a Cauchy sequence, so for every given delta is greater than 0, there exists delta is greater than 0, there exists a positive integer n such that this condition holds good. Now combine this one and this one. It means that because this is less than delta for all, so this is holds good for all n m is greater than or equal to n. That is to say, distance between f of xn, f of xm is less than epsilon for all n m is greater than capital N. It means what? It means that f xn is a Cauchy sequence in M. Okay. Now, the following example shows that a continuous function may not map a Cauchy sequence into a Cauchy sequence. For example, we can consider a metric space with the usual metric x is equal to 0, 1. A metric space x is equal to 0, infinity, open interval 0, infinity with the usual metric inducio on R, and y is equal to R with the usual metric, and define a function f from x to y as f of x is equal to 1 over x for all x in x. And then of course the function f is continuous. Then we can see that xn such that xn is equal to 1 over n, this is a Cauchy sequence in x. But f of 1 over n is equal to n. Okay, the sequence n is not a Cauchy sequence in y. Because indeed the absolute difference of any two distinct points is at least as large as 1. So here is we have this example which says that the uniform continuity is essential in this result. Okay, this result is not true when the function is only continuous. In other words, you can say that the continuous image of a Cauchy sequence may not be a Cauchy sequence, but the uniform continuous image of a Cauchy sequence is a Cauchy sequence. Then we have several exercises. Again, as I have already mentioned several times, that we are putting several exercises. So here is one again we have the exercise, and you have to show that the function f of x is equal to e raised to the power x. That is to say, the exponential function on the usual metric space R is not uniformly continuous. How it is not uniformly continuous? I have given the hint, and you can try by yourself first, and if you could not succeed, then please check. Here is, I have this. Now, another exercise which is also very simple, and say that if f a x d is a metric space and A is a subset of X, then the function f from x to r defined by f of x is equal to dxa is uniformly continuous. Of course, we have proved that this function is continuous. Okay, we have already proved that this function is continuous. Now we will have to prove that this function is uniformly continuous, and it's very simple proof. So by the triangular inequality, you can have this inequality for all a in A and x is in A. Okay, take the infimum over A. So this infimum over A here, and this is independent of A. So leave it as it is. Take the infimum over A here. This is by the definition is equal to dxa. So this is your dxa. Okay, just I would like to mention that sometimes we have mentioned rho xa. The distance from a point x to the set A. Sometimes we have mentioned that dxa, it is same as the distance from a point x to the set A. So rho xa is same as dxa. Okay, so this is holds good, and then we can see that okay, so then you can take this, you can take on the other side, and then we will have, and now by interchanging the value of x, so here is y, here you can take x, here y, here s, you will see that this is also good. That is to say, mod of this is less than or equal to epsilon. So for every given epsilon, choose a delta less than epsilon such that this is equal to this thing, which is less than delta is less than epsilon. That is to say, mod of f of x minus f of y is less than epsilon whenever dxy is less than delta. And now you can see that here is delta is independent of x, and hence f is uniformly continuous on x.